Hi everyone, and welcome to this video on interpreting an f prime graph on a closed interval. Now we've done this before. We've interpreted an f prime graph and answered questions about what f is doing, but we never did it on a closed domain. We did it on an open domain from negative infinity to infinity. And when the domain is closed, you just have to think about it a little bit differently at one of the spots here. So I feel I want to add this video to our collection, especially if you were absent on the day of this lesson. This is a great video just to make sure you're okay. So let's take a look. It says, the figure below is the graph of the derivative of a function f. The domain of f is the set of all real numbers such that x is between 0 and 6 inclusive. Okay, so I start to go through here and I see that they're asking me questions about f. And the hint that I gave you all, the way I like to approach a problem like this, is I like to kind of go off to the side and make my f prime versus f chart. Because to me, if I make this chart, it makes answering these questions so much easier. So this time though, what I'm going to do, we normally draw our number line, but today I want to close off the endpoints, and I'm going to put 0 as my left endpoint and 6 as my right endpoint. And my critical points on the graph of f will occur when f prime of x is 0 or undefined. So I'm looking for where my y values on the current graph I'm looking at, where these y values are 0. So that would be here, f prime is 0 or y is 0, here, and here. So on my original graph of f, which I'm not looking at, I know that the slope of the tangent line to that graph is 0, indicating a critical point at these three values. So I'm going to put those three on my chart. So this is x equals 1, and 3, and 5. Okay, now I'm going to analyze the signs of f prime in between these critical values. So let's look first between 0 and 1. If you look between 0 and 1, let me highlight over that part of the graph. All of the y values, which are the f prime values, are positive. Okay, so we're not looking at slopes here. We're just looking at y values. The y values, which are the f prime values, are above the x-axis, so they are positive from 0 to 1. Between 1 and 3, all of my y values are negative. They're all under the x-axis, so I'll put negative f prime values between 1 and 3. Between 3 and 5, all my y values are above, so they're all positive. And then from 5 to 6, all underneath, so all negative. So what does this tell me about my original function f, which is what they're asking me about in these questions? Well, I know that when the slopes are positive, f is increasing. When its slopes are negative, f is decreasing. Back to positive, increasing. And back to negative, decreasing. So nothing so far looks different. So you might say, Ms. Callahan, why are you making this extra video? This isn't different. Well, but it is. Because this time, when we're answering these questions, we cannot forget these endpoints, 0 and 6. Even though, up until now, critical points always occurred when the derivative was 0. These were your highs and your lows, where the slope of the tangent line was 0 or the tangent line was horizontal. But now, as you leave your left endpoint and come into your right endpoint, these guys on the ends are going to be maxes or mins. We don't know which yet. We haven't analyzed that. But in addition to our interior points here that are critical, we are also going to have to analyze the endpoints for max or min. So we'll get to that in just a minute. Okay, so let's go to question number 1. For what values of x is f increasing? So where is f increasing and why? So my statement there will read something like this. Well, right here. Here's my increasing. Here are my intervals, 0 to 1, 3 to 5. So I'll say f increases on the intervals. Here we go. 0 to 1, union, 3 to 5. Now, why? Well, since the sign of f prime is positive on these intervals. So that's pretty standard to what we've been working on. And if I'm going too fast, feel free to pause the video and write. Number 2, for what values of x is f decreasing and why? Again, reading the chart, you can see that f is decreasing here between 1 and 3, and again between 5 and 6. So I'll say that. F decreases on the intervals 1 to 3, union 5 to 6, since the sign of f prime is negative on these intervals. Okay, good. Now, next question. For what values of x does f have a maximum and why? Okay, well, we know how to find maximums. We need to look for a change in sign that goes from plus to minus. So you see that you go from increasing behavior to decreasing behavior. Increasing, slope of 0 to decreasing. So that's going to be a max there at x equals 1. And again at 5, increasing to decreasing hits another max. So let's start off by stating the obvious. We'll say maxima, the plural for maximum, or maybe we'll say it like this: f has maxima. F has maxima when x equals 1 and x equals 5, since the sign of f prime changes from positive to negative at these values. Okay, so those are the obvious ones. The ones on the interior of the closed interval. Now what I have to do is I have to check these endpoints, 0 and 6. I have to test these because I said they could be a max or a min. So if they're a max, I got to test that out right here on this question. So let's go to these endpoints now and kind of discuss what's happening there. So let's talk about 0. Let's look at the, let me change color here. Let's talk about the right, no, Callahan, left endpoint. The left endpoint is x equals 0. So let's analyze what's happening at x equals 0. So basically, look at it here. As we leave 0, so as we take off to the right of 0, so we're leaving that endpoint, we increase. The slopes are positive, and f increases. So you're increasing out of 0. You're increasing just to the right of 0. Now think about it. If you were graphing your function, f, the original graph, maybe you're at 0, I don't know, -2. We don't know where we are on the y-axis. Let's just say we're there. If we increase out of it, heading upward, f is increasing because f prime is positive. You can see right there, we've got ourselves a minimum. So I am not going to include the left endpoint in my maximum question. Okay. Let's test the right endpoint, which is x equals 6. So my right endpoint occurs at x equals 6. Okay, so let's think about this. If this goes out a little bit further here, say this is 6, and we're at 6, I don't know, negative something or other down here. Let's look at what's happening as we come into that right-hand endpoint. Look at your chart. Just to the left of 6, we're decreasing. So the graph of f is decreasing into that right endpoint. So you're decreasing in, which makes this a minimum. So neither endpoint is a maximum. And so I'm just done right here with this question. But the next question is going to pick them up, because the next question asks, where does f have a minimum in y? Okay. Well, let's state the obvious first. On the interior of the domain, you can see that at 3, the slopes change from negative to positive, decreasing to increasing. So we do have a minimum there. So let's say that first. F has, singular, a minimum when x is 3, since the sign of f prime changes from negative to positive at this value. At this value. Okay. But we also need to state our other two mins on the endpoints. And the way that I justify it, the notation will look a little different, and it'll be right off that pink sheet that we worked on the other day. So what I'm going to say is, so this was kind of like the first one. Here's my next one. F has a minimum at its left endpoint, x equals 0. So there I'm just establishing where it is. Now I'll say why. Since f prime is greater than 0. Now let's look at that. That means the slopes are positive. If you look up here, f prime is positive just to the right of 0. So this is positive for x greater than 0. What you're telling your reader, or me, is that if you leave a left endpoint increasing to the right of that endpoint, it's got to be a minimum. And I'll do something very similar for the last one. We also have a minimum at its right endpoint, x equals 6, since f prime, now let's look at it, the slopes are negative, just to the left of 6, which means we're decreasing in. So f prime is negative, less than 0, for x less than 6. And that's why we know that one's a minimum. Okay, again, pause if you need time to write, and I'm going too fast. Let's flip it to the back. The next two questions are asking me about concavity. Concave up, concave down. Okay, well, concavity is determined by the second derivative. In fact, we determine inflection points when the second derivative is 0. So we set the second derivative equal to 0, and then we find our possible inflection points. We make a chart. So typically we would make that f double prime f chart. We'll make it on our closed interval from 0 to 6, but we need to put on this chart the places where f double prime is 0. So we have to go back to the f prime graph. Now this gets fun. Here's f prime. How do we find out things about f double prime? Well, since f double prime is the derivative of f prime, we need to analyze the slopes of the tangent lines on this graph to find stuff out about f double prime. In this problem, we want to know when f double prime is 0. So we're looking at where the slopes of the tangent lines on this graph are 0. And you can see that that happens at 2 and at 4. So 2 and 4 will go onto our f double prime chart. 2, 4. Now, we will analyze the sign of f double prime in this interval, and this interval. So let's look first between 0 and 2. Between 0 and 2, let me highlight over that. 0 to 2 is here, right there. The slopes on that interval are all negative. So f double prime is negative from 0 to 2. From 2 to 4, slopes, positive. So from 2 to 4, f double prime, positive. And from 4 to 6, back to negative. All right. Well, what does that tell us? This tells us about the concavity of f. So from 0 to 2, we are concave down. 2 to 4, concave up. 4 to 6, concave down. So watch how easy this becomes. For what values of x are we concave up? Well, right here from 2 to 4. So f is concave up on 2 to 4, since the sign of f double prime is positive on this interval. Simple. Likewise, where are we concave down? That would be 0 to 2 and 4 to 6. So f is concave down on 0 to 2, union 4 to 6, since the sign of f double prime is negative on these intervals. There's 2 on these intervals. It's a lot of writing here. Okay. Last but not least, sketch a possible graph of f of x. So here's where it gets fun. So you're going to take all this information and we're going to graph sketch. Now I only have to go from 0 to 6, so I don't really need to draw the negative x-axis, but maybe something like that. So this is going to be x, this is going to be f, the original. And I'll count out 1, 2, 3, 4, 5, and 6. Now, although I'm going to be very specific where I am on the x-axis, I don't know my y values. The thing with the interpretations of these graphs, they don't give us an equation of like f of x. f of x equals blah, 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 blah. We don't have that. So we'll never know our exact y values at any given x value. We only know the behavior of f at these different x values. So don't get hung up, and I told you this before, don't get hung up on where we are on the y-axis, okay? What I do know is this. I like to look at this first chart. I know that something is happening at 1, 3, and 5, and that something at 1, 3, and 5 is that the slope of the tangent lines are 0 there. They are critical points. I increase and decrease and increase and decrease around them. So what I'm going to do is, at 1, 3, and 5, I know that I increase into 1. So I'm going to put that point about right there. And then I decrease into 3. And then I increase into 5. Look at my randomness. I don't even know like why I picked these values on the y-axis. It's just what hit me right now. I know that I start at 0, so maybe I'll start at the origin, 0, 0. Okay, so I increase into x equals 1. I decrease into 3. I increase into 5. And then I decrease into 6, and I stop. Look at that. Random y values, but I increase, I decrease, I increase, I decrease. Now check it out. So I've got horizontal tangent line. See? F prime is 0. F prime is 0. F prime is 0. I've got the two maxima right here. So did I say that there were maxima at 1 and 5? Let's see. Maxima, 1 and 5. Bada bing, there it is. Did I say there was a minimum at 3? Minimum 3. Got it. Increasing, decreasing, increasing, decreasing. Increasing, decreasing, increasing, decreasing. Okay, great. Now, let me check out my second derivative chart. Let's see if this matches up. Do I have inflection? Oh, and one more thing. Wait, before I go to this, do I have minima at the endpoints? Sure do. This is a local min. Look, increasing out creates a minimum. This is a local min, decreasing in creates a minimum. Now let me look at this chart. Okay, 2 and 4 are supposed to be inflection points. Let me mark those on the graph. So like this is supposed to be an inflection point, and this is supposed to be an inflection point. The concavity of the graph is supposed to change at these two values of x. So let's see if it does. From down to up and up to down. From down to up and from up to down. Love it. Totally. Looking really good. So I felt I owed you a video on this, especially if you were out of class. The free response that you're doing for a grade is much like this because it also is on a closed interval. I think it's from like -3 to 5. So hopefully this helps you with that problem because I want you to get that right and do well since it is graded. So thanks for watching and hopefully this helps. See you later.